Okay, now we are ready to face the study of first-order linear equation. This is the topic, but before going into the topics, I would like to tell you something that is not strictly necessary, but can be a good explanation and good information for you. And so I will start now with a remark on the theorem of existence and uniqueness. Which is a very important theorem, the most important theoretical theorem we studied in this part of the course. And let us go backwards and find it. Remember, existence and uniqueness of solution to a Cauchy problem, okay? And so we have a Cauchy problem, differential equation, an ordered differential equation, then n initial data in the correct way, all at the same time, and one for the function, one for the first derivative, up to the n minus 1 derivative. And then there were two conditions on f, on the function f, in the right-hand side of the differential equation. And the first is the continuity of f. I did not insist too much on continuity, on the notion of continuity for functions of more than one variable, but however, that is used in intuition. And the second, it was a more technical function about the growth, the rate of growth of functions. Okay, so when these two hypotheses are fulfilled, then we have existence and uniqueness. So I want to be more specific here. The solution to the Cauchy problem exists and is unique. We also have to say that it exists. Now, a natural question is the following. What happens if we neglect the second, more technical hypothesis and just leave the continuity? And the result is a theorem by Peano that says that the solution exists, but we cannot guarantee that it is unique. And you see that here, in the Cauchy problem with lack of uniqueness, which is the Peano's pencil, the so-called Peano's pencil, we have that the solution exists, but is not unique. Indeed, there are infinitely many solutions. I exhibited the two of them, and then I asked you to find some other solutions. So now let me write this theorem, but with only no, only the hypothesis of continuity of f. So here the mark is the following. Is the theorem on existence This is due to Peano, and this is the theorem of existence of a solution to a Cauchy problem. So consider, as usual, a Cauchy problem where f satisfies this and is continuous. Then there exists a solution to the Cauchy problem. So we have a remark, a first remark that says the solution whose existence is guaranteed by Peano's theorem may not be unique. This is the first remark. The second remark this has to be stressed. I did not stress it enough when we studied the theorem of existence and uniqueness. And the second remark is that such a solution is, in general, let me say, not defined on the whole real line R. So one says that it is local. We know that it is defined on a neighborhood, possibly very small, of T naught. Say something like T naught minus delta, T naught plus delta. Remark 3. The example of Peano's pencil with lack of uniqueness satisfies the hypothesis of the Peano's theorem. Indeed, a solution exists, so existence is not a problem. The problem is uniqueness. Existence is guaranteed. Okay, so this is the what I really wanted you to know, because it is quite important. And now let us go to the second category of differential equation that we want to study, which is the following, which is the class of first order linear equations. First order means that the only derivative is present is the first one. Moreover, we are in the realm of differential equation in normal form. So this is the equation that we want to study, equal to y prime plus a of ty equal to b of t, where the coefficients, we call them coefficients even though they are functions, a and b are continuous functions moreover, and linearity here means that y and y prime appears just multiplied by a function. Y prime, for y prime the function is 1 because the equation is in normal form. So they do not have any power. There is no y square or exponential or so on. So this is a very naive way to describe linearity. This is the structure, linear equation. Then you will have a course about linearity, about the idea of linearity, which is the course of geometry. So don't worry if you don't understand, but this is the shape of the function we want to, of the equation we want to study. And now we have a theorem, which is the following. So the general integral to equation 1 is given by the formula let me write y gen of t is equal to e to the power minus capital A of t that multiplies b of t plus c, where capital A is a primitive of small a, namely the derivative of capital A is small a, and capital B is a primitive of e to the power a of t times small b, namely capital B prime is equal to e to the a b. Okay, this is the formula you have to you have to learn by heart, basically. Of course, you know that I don't like that people, especially young people, they have a very good memory, but I don't like that you learn something by heart. I like you learn at least a reasoning to reconstruct it. However, this is a formula that it is so from one side so ugly, so horrible, so lousy that so it is not really a pleasure to remember it. On the other hand, if you study it by heart, then you go faster. There is really nothing deep, to my knowledge, to or nothing clever to associate to this formula, so you can just adapt yourself to this situation and study it by heart. Otherwise, you can deduce every time you need it, and it is not very difficult to deduce it. And this is what we do here to prove the theorem. Sorry, you hear strange noise, but don't be afraid. Everything is under control. Okay. So let me give you the proof of this horrible formula. And first of all, introduce a new function. So let us introduce the function z of t is equal to e to the I of t y of t, where capital I is a primitive, whatever primitive you find, any primitive of small I, so that capital A prime is equal to A. Then you end up with y of t is equal to e to the minus a of t z of t. Now, write down the left-hand side of the differential equation. So, y prime of t plus a of t y of t is equal to what? Is equal to e to the minus a of t z of t prime, this is y, plus a of t e to the minus capital A of t z of t. Now, compute this derivative here. It is immediate, so you have minus a of t, which is the derivative of capital A, so minus a, and then e to the minus a of t z of t. And here we differentiated this factor. Now, by Leibniz rule, we have to differentiate the second one, e to the minus a of t z prime of t plus a of t e to the minus a of t z of t. And here there is the miracle. The miracle is that these two terms cancel each other. And of course, now this is the first member, the left-hand side of the equation, which is equal to the right-hand side. So we end up with this nice fact that z prime of t equals e to the power a of t b of t. Then z of t, just integrate. If you want, this is an indefinite integral of a very easy differential equation. And strange noise. Okay, I don't know if you hear this noise. They are strange. And very strange noise now. Don't be scared of my noise, that it is an emergency. Horrible noise. Sorry for these noises. So z of t is equal to what? Is equal to the integral, indefinite integral, because we are looking at the general integral of the equation, e to the power capital A of t, b of t, dt, and by definition of capital B is capital B of t plus c, where we define B of t is a primitive, any primitive, of e to the power A of t, B of t. Now here we found z, and now we have to go back from z. We have to go back from z to y. So we end up with y of t, which is equal to e to the minus capital A of t, then z, which is b of t, capital B of t plus c. So, as an exercise for you, show that the formula, the expression for y gen, does not depend of the choices, on the choices, dependent on, independent of, depend on the choices of A and B. There is some arbitrarity, but the general formula does not depend. And now let me give let me give the time to do some two exercises. So exercise 1 is find the general integral of the ODE y prime plus xy is equal to e to the minus x squared over 2 cosine of x. And of course, here you have that a of x is equal to x, so capital A of x you can take x squared over 2. Then b prime of x is equal to a of x, a to the power a of x, e to the power a of x, and then b of x, so e to the power x squared over 2, and then e to the power minus x squared over 2 cosine of x, and this is cosine of x. And so as b of x, capital B of x, you can take sine of x. Applying the formula by the theorem, we have that the general integral y gen of t is equal to e to the minus x squared over 2 e to the minus a of x, and here sine of x plus c. Notice that c here does not appear as an additive constant. It's an additive constant times this guy here. So another collateral exercise to this is the following. Solve the Cauchy problem here you have y prime plus xy is equal to e to the minus x squared over 2 cosine of x, so the one before, and then y of 1 is equal to e, for instance. Okay? So we already know that the general integral is equal to e to the minus x squared over 2 sine of x plus c. So y of 1 for our solution must be e to the minus 1/2 sine of 1 plus c, and this has to be imposed to be equal to e. So we have that c is equal to e minus this is a parenthesis here, this is a bracket. So c is equal to e to the power 3/2 minus sine of 1. Then y of x, in this case, we called x instead of t the variable here, is equal to e to the minus x squared over 2, and here we have sine of x plus e to the power 3/2 minus sine of 1. This is the unique solution to the Cauchy problem. And notice that it is global. This was not guaranteed a priori. Okay, and this is all for this category of differential equation, and in the last lecture we will meet the last class of differential equations we are interested in.